Our last unit will be residual management. So when we're talking about residual management, we'll just look at some principles of residual management, solids computations, and then we'll look at sludge types and the characteristics of those sludge. How do we manage this material? And then ultimately, how do we dispose of it? Taken from a colleague's slides. Absolutely correct. There is no free lunch. And almost every process, every activity at a wastewater treatment plant produces some sort of a waste stream. If it's recycled, then where you can recycle it, how it's recycled depends on its quantity, its quality, and the needed treatment. And we'll talk a little bit about the filter backwash recycle rule. This is important. It's extremely pertinent to drinking water systems where you have filtration and you're recycling that backwash. So let's just look at this process here. See if we can kind of think through it. This is actually a schematic for a parallel conventional and membrane filtration plant. It's from chapter 6 of the textbook. Where are the residual or waste streams? It's not drawn on the figure.
The sedimentation basins, the filters,
okay, so,
membranes.
Okay, so we've got sedimentation basin, we've got sludge, right? We've got filter, we've got backwash here. We have sludge here. We have our concentrate here. Mentioned with fouling that we often have to clean the membranes to reduce fouling. So we have those what we refer to as clean in place chemicals. We also likely have off gas from the ozone contactor that would have to be dealt with before it's released, because we can't release ozone out into the atmosphere. So we'd have to degrade that before we release it. So we have a number of, just in this, what looks like a simple diagram, a number of processes that will result in some sort of residual that we'll need to deal with. This is a schematic showing how we deal with it. Much more complicated than just an arrow off on the schematic. So basically, if we think about this and what's shown here, so for instance, with this conventional filter backwash, we have water that contains solids. We perhaps could treat that, and we'll talk about these, but by dissolved air flotation, that's DAF. We could use gravity thickening. We then have some sort of supernatant that we need to deal with. So notice this is shown as recycled to the conventional train, so that typically will go to the headworks of the plant. You may have a sludge lagoon for drying, other processes that we could use. Then we have the membrane backwash. Here it's shown with, again, as dissolved air filtration. It could also be gravity thickening. It could be, depending on the membrane itself, you may have if it's an RO or nanofiltration, you've got a high salt content, and you have to think, and we'll talk about that, we talked briefly too with membrane filtration, that we have to dispose of that safely. This is just a list of some of the types of solid liquids that are generated in a treatment plant. So you mentioned that backwash water that could be treated, that may be untreated. We have the clarifier, and so We could have chemical sludges. We could have polymers in the sludges. We have softening sludges with wastewater. We have primary, secondary sludges. We may even have tertiary sludges. We can have a gravity thickener. We can have spent activated carbon. We could have spent alumina. We could have a sludge lagoon overflow. So there's a whole variety of different processes that will generate a solid liquid stream that has to be dealt with. We also can produce liquids. So we have an ion exchange regenerant brine. We may have waste regenerate from an activated alumina system. If you're looking at reverse osmosis, you've got that concentrate. Mention the clean in place liquids. And then we have gases. If we're using air stripping, we have air stripping off gases. If we're using ozone, we have the ozone off gases. And you have also malodorous compounds, you have aerosols from the aeration basins, and you'll find in some cases, especially where these basins are very close to dense populations, you'll find that these are covered, and in some cases, those gases are actually treated before they are released to the atmosphere. So just looking at some of the equations, we've done some of the volume calculations, but just as a review, the volume of your solids is equal to the mass of the solids, and this is a dry weight, divided by the density of the solids, which is equal to the specific gravity of the solids times the density of the water. Now your sludge, we can assume, is made up of just solids and water. And given that, then the mass of the sludge is just equal to the mass of the solids plus the mass of the waters. We're going to assume that there's no interactions between the solids and water, so that we can also say that the volume of the sludge is simply equal to the volume of the solids plus the volume of the water. And that makes things a little bit easier, and it's, in terms of calculations and designs, this is sufficient. Then we can just represent then the relationship between these two parameters using the density of the solids, so the density of the solids, the density of the water. We'll assume that the specific gravity of water is equal to 1. And you can see here we have the specific gravity of the sludge itself. Typically, the solids content is reported as a weight fraction. So the fraction of solids is just the mass of the solids divided by the total mass, which we've said is solids plus water. And then the fraction of the water is simply the mass of the water divided by the total mass, which again is just the weight of your solids and your water. I'm not going to derive this next equation. It's just simply based on the basic mass volume relationships that we've used, but the specific gravity of your sludge is simply equal to the specific gravity of the solids divided by the fraction of the solids plus the specific gravity of the solids times the fraction of water. And then the volume of the sludge is simply equal to the mass of the solids divided by the density of the water times the specific gravity of the sludge times the percent of solids. So we'll go through an example of this so that we can use these equations again. And you can then, you've calculated your masses and volumes of the sludge produced during sedimentation of your raw water. So you have a sense of that. You have backwash water in your system that you're designing. So you can think about how might you treat and dispose of these waste streams. When we look at wastewater sludges, we typically refer to them as having both a fixed and a volatile fraction. So this is predominantly with wastewater. So that fixed sludge is the inorganic portion. The volatile is the organic portion. And similarly to what we just did, where we looked at mass of the sludge and we looked at mass of the solids plus water, here we're going to divide that mass of the solids into these two fractions. So our fixed inorganic and our volatile organic fraction. Why would we do this? This fraction here is predominantly in your wastewater sludge, organic material, and if it's a secondary sludge, it's predominantly microorganisms.
So could that be variable to change if they like proliferate or something?
One, variable in terms of how they change, but they also variable in terms of density. Your microorganisms are much lower density. In fact, they are often slightly less dense than water. So they tend to want to float. Your inorganics are much heavier, so they're much more dense. So how they behave is actually quite different. So for that reason, often when we talk about these fractions, when we talk about disposal, treatment and disposal, we divide them into the inorganic and the organic fraction. The specific gravity of the solids is related to the specific gravity of the fixed solids, the volatile solids, and then divided by the sum of the mass of the volatiles times the specific gravity of the fixed, and the mass of the fixed times the specific gravity of the volatiles. And we could take those previous equations and derive this equation, but I'm not going to do that. The textbook actually does go through the derivation. Okay, just looking at some of the types of sludges, and I'm not going to spend a lot of time kind of going over actual values, but I want to go through the different types of sludges. So for example, if we're treating a surface water and we use pre-sedimentation, so for instance, to remove the more inorganic material, typically this would be sand, then you've got pre-sedimentation and you have those solids from the pre-sedimentation. You then have the coagulation. If you're treating a surface water and you're coagulating the suspended solids, then you have the type of sludges that we just calculated. These usually are your chemical solids, typically hydroxides, and then whatever suspended solids that you've removed, and this can be clay, silt, it can be organic matter. Typically, you're looking at sludges that contain from about 0.5, less than 1%, to about 4% solids. And that will depend on the initial turbidity and the coagulant used. And typically, somewhere between 20 to 40% of your solids are organic. Why is this important in terms of thinking about processing this material? If they're organic, they can potentially degrade. If they degrade, they can consume oxygen. If they consume oxygen and it goes anaerobic, what happens now?
By anaerobic, do you mean septic?
Yeah,
Like,
exactly.
'cause it's
Yeah.
okay.
So lacking oxygen. So here's where you're going to potentially produce hydrogen sulfide. You can produce methane. You can produce CO2. Various malodorous compounds. So the higher the organic matter, the more potential you have for this. It's not typically all that common with water treatment sludges, but if you have a high organic content and you're holding this sludge for any length of time, it can go anaerobic. Specific gravity will vary. Typically for alum sludge, it's about 1.2 to 1.5, a little bit higher for iron sludges. And typically your pH of these sludges are slightly acidic. Now, if you're looking at softening sludges, these tend to be, as we looked at earlier, predominantly calcium carbonate and magnesium hydroxide. Not surprisingly, your pH is quite high. So with softening sludges, you're dealing with a very alkaline sludge. With coagulation sludges, your alum or iron sludges, you're dealing with an acidic sludge. Specific gravity is higher of the solids or higher for softening sludges than it is for your alum or ferric sludges. And because of that, your solids content is also higher. It settles better. You also can have iron and manganese precipitate. So this is, for instance, with an iron manganese removal plant, similar to that at MSU. Typically, the volumes of these are low. You're looking at oxidation and precipitation of the iron in the groundwater. So typically the solids are captured on the filters, and therefore they will be in the filter backwash. So if you think back at the MSU system, you have those big filters. You don't have any solid separation. So where does the filter backwash water go? So for the MSU system, that's an iron and manganese removal. You saw the filters. They backwash the filters. Where does that backwash water go? In the case of the MSU system, it's going to go to the sewer. Okay. So they actually have to have a permit to discharge because that becomes an industrial pretreatment process. So your spent filters backwash typically is about 2 to 3% of the total plant flow. So that's pretty significant. If you're talking about, for instance, the dye plant, that is a 40 MGD plant. 2% of that is pretty significant that they have to deal with. So at the dye plant, they can actually treat that and then recycle that back to, so that can go, for instance, I believe it goes into the gravity thickener, and then that supernatant goes back to the plant. And it can contain 10 to 20% of the total solids production, so it can be significant. Suspended solids can range from 30 to 400 milligrams per liter. And this is important. It used to be that the filter backwash could be discharged back into the receiving body of water. So for instance, in your treatment plant, so think about this in terms of mini design 3 and how you're going to have to address this. You're treating water from what sources?
Both groundwater and surface water.
Both groundwater and surface water. So if you're treating water from surface, if there's any surface water, the surface water treatment rule is applicable. The filter backwash water recycling rule is designed to protect the receiving body of water from receiving water with concentrated concentrations of Cryptosporidium and Giardia and other pathogens. So it requires that recycle streams actually pass through all of the processes of an existing conventional or direct filtration system. So for your plant, what does that mean? What's the impact? I'm not going to answer that. I want you to think about it. And you'll need to address that in that final report. You have a surface water, that surface water, because it's a surface water system, the filter backwash recycling rule is applicable.